Okay, part 3. So we have been talking about nearest neighbor, Ripley's K, oh, we didn't, but I mentioned it, and kernel density estimates. And these can all be used to determine spatial distributions and patterns based exclusively on the feature or the event locations, right? So now we're going to talk about tools that will help us understand the degree to which near and distant things are related based on the similarity of their attributes or the values associated with those locations. This is cool stuff. I mean, the other stuff is cool, but this is cool too. So first of all, spatial autocorrelation. Who has heard of Tobler's first law of geography, right? This is the concept that near things are more related than distant things. Well, first of all, that isn't Tobler, this is Tobler, Waldo Tobler. And his first law of geography states that everything is related to everything else, but near things are more related than distant things. And hopefully you can see from this somewhat simplified figure that we're talking about more than just simple spatial location. It's the attributes or values associated with the location that are also relevant to the relationship. Such a friendly, modern guy. Whatever. Okay, so but first we have to talk about the modifiable areal unit problem. I would be completely irresponsible if I got through the whole semester without at least mentioning this. It's one of the better known problems in geography and spatial analysis. It's basically a concept illustrating the need for considering area and space in our analyses and the uncertainties that underlay the analyses we perform about the real world with spatial data that's fundamentally, well, manufactured or in some way generalized. There is an inherent disconnect between reality and the way reality is conceptualized with digital data, and I hope that I've made that point really clear to you guys already. But I think this is a really good example of that because you can't help but organize and generalize your data, and every time we do that, we are, we're fundamentally changing the kind of real message or the real story that's happening. So let me just back up. Basically, this concept refers to the problem of imposing arbitrary boundaries on normally continuous geographic phenomena. The results of our analyses are going to be sensitive to the size or shape of the zones that we impose to organize or aggregate the data. So in this example, imagine that these red dots are underperforming schools and the black dots are meeting or exceeding standards. Schools that are, not the dots. The top figure is basically organized in a way that if we were to summarize it with statistics, it would reveal very even distributions of overall performance per school district, right? So each district is performing slightly above standards because we have 3 that are meeting or exceeding and 2 that are underperforming. So each district looks pretty good. But what if we drew the lines this way to define the school districts? Now we have basically a delineation that reveals these extreme clusters of overperforming schools and clusters of underperforming. And so the districts would be completely differently defined just from the way we drew the lines, right? So this is also true if we treated these data points in raster format as a continuous surface. Hopefully you can see then that the cell size would start to dictate how the points are aggregated. And so we're always going to be imposing some artificial structure on the data. And it's almost impossible not to do that. So again, one more thing you just need to keep in mind when you're dealing with spatial data. So just to drive the point home, think of gerrymandering. Gerrymandering is, basically reshaping voting districts based on political affiliations of citizens, right? To deliberately create numeric advantages for one political party or another. And I'm not saying that anybody does this. You can see here in this top figure, this is how fair districts might be drawn. There's an equal number of registered voters for each party. But just for example, if the Republicans wanted to have an advantage, they might want to redraw the lines so that more districts have a majority of registered Republicans, and it might look like this. And this happens all the time, and it happens on both sides. It's not a Republican thing. I don't mean to pick on anyone here, but here we've got a dominant Republican registered voter group in 5 of these, and one that's just heavily Democratic. But then, anyway, you know what I'm talking about. I'm going to move on here. When we impose these kind of organizational boundaries on data that isn't physically or otherwise constrained by that boundary, we are by definition altering the system, right? And I think that's the take-home message here. It can result in artificial results, artificial identification of spatial patterns, and misidentification of spatial phenomenon. So, yeah, just keep it in mind. It's a deceptively obvious problem too. I think that's the hard part. The conclusions that you draw are going to vary depending on how you choose to spatially organize and classify your data. So just keep it in mind that the way you interpret a landscape is going to depend on where you draw the borders and organize it. And anyway, so that's what the modifiable area unit problem is, and no more about that. So spatial autocorrelation. The GIS dictionary tells us that it's a measure of the degree to which a set of spatial features and their associated data values tend to be clustered together in space, which is a positive spatial autocorrelation, or dispersed in space, which is a negative spatial autocorrelation. This is very different than hotspot analysis, and I'll talk about that in a second. So we're basically talking about the correlation of a variable with itself through space. And one of the main reasons that spatial autocorrelation is important is because statistics rely on the assumption that observations are independent from one another. So if autocorrelation exists in your map, then your data is already violating the fact that observations are supposed to be independent from one another. So we do need to identify this to move on with other kinds of analyses. So how are we going to measure it? We're going to use a tool called Morans eye to start with. Morans eye is different than bird's eyes and bull's eyes. Definitely not the same thing as the eye of Sauron for all you Hobbit nerds out there. And it's also, wait for it, different than this, the eye of the tiger. You knew I was going to pull this at least once. Yeah. Okay, so enough of that. This is Moran's eye. This is Pat Moran. This is his eye, but not his actual eye. It's a Moran's index. It's basically the most common measure of spatial autocorrelation that we have. Moran's eye tells us basically how related values are based on the locations where they were measured. So the values associated with the locations. It tells us whether the pattern of feature, it tells us whether the values of features and the pattern of them is clustered, dispersed, or random. So just like point pattern analyses, the output of the Morans eye test can be classified as positive, negative, or no spatial autocorrelation. But again, this time we're talking about the values associated with the spatial locations, not just the locations themselves. So positive spatial autocorrelation is when similar values cluster together in a map, and negative spatial autocorrelation is when dissimilar values are proximate in a map. So if the neighbors all tend to be very different in value, that's considered a negative spatial autocorrelation. So really quickly, I want to draw your attention to the conceptualization of spatial relationships input. This is another time when you really want to have the tool help open and read about these things. I just want to go over a couple of them really quick. You can look them up in the ArcGIS resources. It's one of my favorite things. I have my interweb handy at all times when I'm running tools like this for the first time. So just a quick explanation of the options. So one of them is inverse distance, and this means that all features influence all other features, but the closer things are, they have more influence on the results. Distance band is another one that's in here, and that means that features outside of a specified distance don't influence the features within that area at all. Kind of just gives you a little buffer. And that might be really important if you have structures on the landscape that actually prevent influence from features, whether it's terrain or roads, things that would prevent things from connecting on the landscape, basically. A zone of indifference is another one, and it combines inverse distance and distance band, kind of gives you a weighted method of doing both a little bit. So take care with these things and read up on them. I guess that's always the moral of my story here. Moran's eye, the tool produces 3 outputs. We get a Moran's eye index value, kind of like the average nearest neighbor. We get a z-score and a p-value, which again evaluates the significance of the index results. If we end up with a positive index value, that indicates clustering. Values close to 1 indicate negative, or sorry, close to -1 indicate negative correlation or dispersion. And when the index is close to 0, that's the random distribution. So, when a p-value is really small and the z-score is enough to fall outside the confidence level, then the null hypothesis can be rejected for those of you stats people. In other words, for those of us who aren't, the data shows a pattern that's too unusual to be a pattern of random chance, and there is spatial clustering of values associated with the geographic features in the study area. All right, so here's an example of that, a couple of examples. In the top, the polygon values might represent mean household age, for example. The Morans index is negative 0.12, which means the values are slightly dispersed. This might tell us that there isn't a spatial pattern to explain the distribution of mean household ages, right? In the bottom map, the Morans index is 0.26, positive, which means the values are exhibiting slight clustering. Near features are more related than distant features. The index doesn't differentiate, though, between high feature values and low feature values. It just indicates whether or not near features are similar. I think that's really important to note, too. Hotspot analysis is some pretty cool stuff, and I think the one thing I want to make really clear, well, let me start at the beginning. So hotspot analysis tells us where clusters of high values and clusters of low values exist. So with Morans eye, it doesn't differentiate on the kind of values, just if they're similar or not. But with hotspot analysis, the hotspots are clusters of high values, and cold spots are clusters of low values. So cold spot doesn't have anything to do with dispersion or non-clustering. It is a hotspot of low values, if that makes sense. So in order to be statistically significant, a hotspot has to have a high value and be surrounded by other high values. A cold spot is going to have a low value and be surrounded by other features that have low values as well. So don't think of a cold spot as kind of like with the random or uniform distribution. It's basically a low value hotspot. The output from the hotspot analysis tool is a z-score and a p-value for each feature. And these values represent the statistical significance of the spatial clustering of the values. But again, these values are highly influenced by the boundaries that organize the data, the enumeration units. You know, in our case, the way you choose to conceptualize the spatial relationships. So remember what I was just talking about with the inverse distance, the fixed distance bands, and also the scale of the analysis, right? These things are all going to greatly impact the results that you get from hotspot analysis. So you might want to experiment, if you're doing this for your research, with different kinds of enumeration units, in addition to messing around with the different spatial conceptualization of spatial relationships. So if we have a high z-score and a small p-value for a feature, indicates a spatial clustering of high values. If we have a low negative z-score and a small p-value, it's going to indicate a spatial clustering of low values. So here the z-score, we're not thinking about the absolute value, we're actually going to take it, and that's how the hot and cold spots are identified. The higher or lower the z-score, the more intense the clustering is, and that should make sense. And then again, a zero z-score or a z-score nearing 0 indicates no kind of spatial clustering at all based on the values. This is what it looks like. It's going to help us answer questions like, where are we seeing unexpectedly high crime rates? Or where are we seeing unexpectedly low high school graduation rates? Those would be cold spots. The hotspot analysis tool works by looking at each feature relative to its neighbors. And again, if the value for a feature is high, that could be interesting by itself, but if the value for a feature is high and the values for neighboring features are also high, that's what makes it a hotspot. So say you want to determine where there's a high incidence of animal roadkills to identify potential locations for wildlife crossings. You could run hotspot analysis on the raw incident counts And this, would that be an interesting thing to do? It's really useful for resource allocation issues. Or I found an example about foreclosures. You'd probably expect more home foreclosures in locations with more homes. If you divide the number of foreclosures by the number of homes, you are essentially normalizing the data. And then if you run the hotspot analysis tool on this normalized data, and then you're going to get an answer that tells you where there are unexpectedly high numbers of foreclosures given the number of homes, instead of just simply knowing where there are a lot of foreclosures. So this is going to be really relevant to our Bigfoot analysis. We can control for expected relationships. Would we expect to have more sightings in places where there are more people? Well, yeah, maybe, maybe not. So again, it's considering your inputs, considering your outputs, evaluating yourself, having some idea of what to expect, and yeah, don't accept any of the defaults. So just as a quick reminder, there are a lot of extensions that aren't preloaded in ArcGIS. Remember, if you're up in the lab, that you need to go in and set these extensions, turn them on, activate them every time you log on. And there are a lot of tools in if you right click at the top, there's a whole list of toolbars that are available to use. And don't forget about the geostatistical analyst. I mentioned this a couple weeks ago. There are all sorts of great tools and ways to visualize your data, and just make sure that we are dealing with the assumptions. And that's pretty much it. If you have questions, let me know. Thanks for bearing with me. It's a pretty dry subject, but I think you'll have fun working with this week's data set. All right, so that's it.